In this video, we're given a position vector for a particle. That's r of t is negative 3t plus t squared times I hat, plus a 1 minus t times j hat. And we're told we can assume all of these coefficients in front of the unit vectors have the correct units so that everything comes out in meters. In part A, we want the instantaneous velocity and acceleration vectors evaluated at t equals 1 seconds. So we get the velocity vector as a function of time in general by taking the time derivative of the position vector. And that means we just differentiate each of those coefficients of the unit vectors with respect to t. So my first coefficient is going to come out to negative 3 plus 2t, and that multiplies I hat. And my second coefficient is just the negative 1 times j hat, and I can just write minus j hat. Then I can evaluate this at t equals 1, and I get my velocity vector at t equals 1 second. So you just plug in a 1 for t, and my coefficient of I hat here would become a negative 1. And my coefficient of j hat doesn't have any time dependence, so that's still just negative 1. And if I put units on this, I could write it as negative 1 meters per second I hat minus 1 meters per second j hat. In other words, at this moment in time, the particle is moving simultaneously to the left at 1 meter per second and down at 1 meter per second. Now I continue to get my acceleration vector, and that's just the time derivative of the velocity vector. So I just differentiate these coefficients with respect to t one more time, and I get a 2i hat. And let me back up and just indicate for the previous line that I was evaluating the velocity vector at t equals 1. So back to my acceleration vector, what I notice about it is that that's a constant. There's no time dependence to my acceleration vector, and that means no matter what time it is when I evaluate this, and I'm going to do that at t equals 1 second, I just get 2i hat for the acceleration vector, and if I put units on this, it means 2 meters per second squared, or 2 meters per second, pointing exactly to the right, and that never changes for this particle. Part B is interesting. I'm asked to use the dot product to determine whether the particle is speeding up or slowing down at t equals 1 second. And what I'm getting at here is that the relative angle between the acceleration and velocity vectors determines whether or not I'm looking at something that's speeding up or slowing down. And I made a whole video for this, and I'll post a link to it real quick. So in the first picture I just drew, this sort of generic acceleration and velocity vector for a particle. The acceleration points partly in the same direction as the velocity, and this actually causes the speed to increase. The other possible case is when the acceleration partly points opposite to the velocity vector. And in that case, the parallel component of the acceleration vector points exactly in the opposite direction of the velocity. That's going to cause the velocity vector to decrease in size, and this object is slowing down. So how can we use the dot product to determine which one of these cases we're looking at? Well, in the first case of speeding up, the angle between the acceleration and velocity vector is less than 90 degrees. And in the second case, where the acceleration is partly opposing the velocity, that's an angle bigger than 90 degrees. And this just changes the sign of the cosine theta in the formula for dot product. So A dot V is the product of the magnitudes, A times V, times the cosine of the angle between the two vectors. And the cosine is going to be positive as long as that angle is less than 90 degrees, and then the cosine becomes negative if the angle exceeds 90 degrees. So we just compute the dot product, and then we look for the sign of the result, and plugging the vector components in to get the dot product here. A dot V is going to be a 2 times negative 1, plus, well, the j hat component of A is 0, so that's 0 times negative 1. And I get a negative 2 for this. And then I realize that a negative dot product means the cosine piece is negative, and that means the angle is bigger than 90 degrees, and that means this object is slowing down. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.